Hello, welcome to Module 9. This is about nuclear power. We're talking in Chapter 14, and this is actually video part 4. I know that there will be a lot of videos for this specific subject matter, and I apologize for so many videos. This is just a topic that needs to be covered well, and the book gets to be a little outdated as far as text, so you can't lean as heavily on text, and I really want to make sure that I give you guys a very complete knowledge. So, talking more about fission, we left off just talking about uranium and how we're going to utilize uranium to produce electricity, and that we like to use uranium because it's easy to manipulate. I can manipulate uranium, specifically the weight of uranium-235, very easily by bombarding it with one neutron, which fluctuates its weight into the 236 range. So it keeps its 9 protons, but it gets up to a 236, which makes it unstable. It can't exist naturally at 236 or 237, and therefore it will break apart, making krypton and barium and throwing away some extra neutrons in doing that. With that said, uranium naturally comes in uranium-238. That is the most common form of the uranium set, and that something as light as uranium-234, which is considered lightweight uranium, and uranium-235, which is considered middleweight uranium, does exist, but it exists in very small percentages. Less than 1% of your average uranium rock will contain that very rich, easy to manipulate, good to produce electricity form of uranium. As far as keywords, one of the keywords you need to know is chain reaction. A chain reaction is when I take that neutron and I bombard it with a atom that is unstable, like uranium-235, and when it splits, it throws off extra neutrons that it doesn't need. And those neutrons then hit into more uranium-235 or any radioactive material, and it causes them to split. If I can split and go from one generation to another generation of splitting, and I can do this at least 2 times, I have what's called a chain reaction. Which brings me to critical mass. Critical mass is when I reach a point where they are splitting, so the atoms are splitting, making 2 new elements, so they're splitting apart, but I can no longer rein in the neutrons in the atom splitting, so that it will reach a point of critical mass and continue its chain reaction until it runs out of material. And so there's no going backwards from critical mass. Hence the statement critical mass. That's where that terminology comes from. I cannot stop the chain reaction when I've hit critical mass. So going into uranium itself, it's known as uranium-235. That is specifically the one that we want. If you look at the periodic table of elements, obviously its atomic number is 92 because that's how many protons it has, but its atomic weight is normally written as 238, and that's because that's how it's most likely to occur naturally in the environment. I have the melting point, boiling points, but we won't be using either one of those. You're going to find it as a solid. It's a metal, but it's a yellowish colored metal. And it has a half-life of around 4.4 billion years. And it decays into thorium, which also has a alpha decay ability. So it becomes another radioactive material when it tends to break down. Uranium-235, which is the one that I'm looking for and I want to find within the uranium rock itself, because that's the one I can manipulate. That's the one that I can make unstable and decay on command, basically create its radiation on demand. That occurs at only about 0.7%. So like I said, less than 1% of the time. There is an advantage to using uranium, and that is the amount of energy that I get out of uranium is extensive. 35 tons of uranium, and I use 35 tons because that's the average uranium reactor core is loaded with about 35 tons of uranium. Hence, when I'm using that, can produce 90,000 megawatts per year. And when I fill my reactor core with that amount of uranium, I do not refurbish or replenish the amount of uranium in my reactor core until I use it all up. And that takes about a year to use, but sometimes longer. And so my average core is about 35 tons worth of uranium, and it takes about a year, sometimes a year and a half, depending on location. Compare that to coal, it would require me 3,000 tons of coal to produce that same amount of energy, or 14,000 tons of crude oil. And just to get a handle on how much this is, one of these train cars is 55 tons of coal. And this little tankard right here is 28 tons of crude oil. So this is 1 kilogram's worth of a uranium pellet, and that is equivalent to this, which is equivalent to this. And so it's quite astounding how much energy is packed in nuclear reactions. You think of suns like our star, like stars, our sun is a nuclear reaction. We are doing fission and fusion all the time. So it's a huge amount of energy. The fuel cycle goes from mining to conversion. So I have to find uranium 235 out of what I have mined. Enrichment, fuel fabrication, power plants, reprocessing, and storaging and disposal. So mining is step 1. In the United States, we now prefer to do open cast pits, which is pretty much strip mining again. It's a little bit different because of the nature of uranium. We want to be safe about it, but we do open cast pits for uranium mining, which is very much like strip mining. And we don't do underground mining anymore in the United States. It's just not safe. But if we're getting our uranium from other countries, which we do, we totally get it from countries that still do underground mining. As far as where are our uranium stores in the United States, most of them are located in Wyoming, Texas, Colorado, New Mexico, and Utah. And we're pulling it right out of the ore within the rock. And when we pull it up, we pull out the rock, we then enrich the rock or break it down. And what we're left with is a powder. And the powder of the rock, or the rock powder that's left over, happens to be uranium oxide, or UO2. Interestingly enough, it looks exactly like Betty Crocker's yellow cake mix. And so in the industry, we just call it yellow cake as it's there. So here's an open cast pit. And here is a facility that was once a cast pit, which is now an abandoned uranium mine. And just the little artist graphic. Here is some old-timey pictures of underground. And like I said, we don't do underground much anymore. Here is how, if we are doing underground, or even if we're done with a facility, so it's a cast pit, but we're done with it and we're no longer going to use it, we have to set up these mitigation areas where we can check to make sure that we're not polluting groundwater and such with radioactive material. And here's the uranium oxide after it's been pulverized. So after we've pulverized the rock down, it's left looking like yellow powder. As far as uranium mining, like I said, we're not a big number. We're about 4% of the world's uranium stores, but you can see who has the most and where we're getting it from. Which brings us to getting that powder and turning it into something more. So enrichment. When we pull up uranium oxide, only about 0.7% of it is the 235 we need. In order to create the little pellets that we use and load into reactor cores, we actually have to turn that 0.7% into a 2 to 3% raise. So we have to filter out some of the uranium-238, not all of it. Like I said, I only need 2 or 3%, and that's a good number because it keeps the uranium at a level where it is radioactive and able to produce huge amounts of energy. When it's breaking apart, it's producing huge amounts of heat. But at the same time, it is not going to produce enough energy or enough heat to create a bomb. Our reactor plants cannot go or explode. So on that note, I'm going to pick up talking about the 3 forms of enrichment in the next video in a part 5.